All right, today we're going to look at the first lecture of chapter number 4 and the learning goals for today. The first one is understand the meaning of a force in physics. The second, recognize the vector nature of forces and learn how to combine forces. And the third, learn the significance of net force on an object and what happens when the net force is zero, and that's known as Newton's first law or the first law of motion, and when the net force is not zero, and this is known as Newton's second law or the second law of motion. Now, an overview of forces here. We have two kinds of forces. We have what we call contact forces, and we have what we call field forces. If in chapter 2 and 3, we describe kinematics in 1, 2, and 3 dimensions, but we did not really say what caused the motion. You really have to apply forces to cause these motion, and you always have to make contact. So, for example, you see here a hand pulling on a spring. You see a mother pulling a child on a small cart. You see a player kicking a ball. And all of these, there is a contact force. That means there is a touch, okay, direct contact with the object. Now, there are other forces which we call field forces, and something that you're familiar with, and we already talked about free fall in 1 dimension, and we call that free fall. In 2 dimensions, we said that this is a projectile motion, which is under the action of gravity. Anything that you raise above the surface of the earth, it will fall toward the surface of the earth, and you do not see any contact, but there is something pulling on. And this is what we say, that we have a gravitational field, and in this case we call this gravitational force. It could happen also between electrical charges. In the case of electrical charges, in the case of a gravity, it's always pulling, so it's an attraction. But in the case of electrical forces, you may actually repel or attract depending on the charges are being both positive, they repel. Being both negative, they repel. When they're opposite, the charges that mean negative and positive, they will attract. And what's operating between both of them is an electric field. Magnets, and I'm sure that you played with magnets. A magnet usually have a north pole and a south pole, and you can play games with them. You can chase one magnet with the other. If you put north facing north, that means they're going to repel. Or you can basically, without touching, you can make magnets attract. That's when north is basically facing south on the other magnet. And this is what we call magnetic force, and what's operating between both of them is magnetic field. So these are field forces and contact forces. You are basically, in your daily experience, you deal with contact forces a lot, and you can see the effect of gravity, which is basically a field force on daily basis. Is this clear? Any question on this? So these are two kind of forces that we can deal with. Here we're going to deal with some properties of a force A force is a push or a pull. So you have an object here, and you're pushing on the object by applying a force, or you're pulling on the object by also applying what? Applying a force. So a force is always a pull or a push, and this is what you do with contact forces. In the case of field forces, the Earth is pulling, but it's pulling through a gravitational field on the object. And in the case of electrical force, you may actually push or pull, but it's that done by electric field. And in the case of magnetic fields, the same thing. You can either push or pull, and that is mediated by a magnetic field. A force is an interaction between two objects or between an object and its environment. A force is a vector quantity with magnitude and direction. And we already dealt with vectors. So these are basic properties when it comes to a force. So we talked about a force is a pull or a push. We talked about contact forces, field forces, and the force usually is interaction between two objects or an object with its environment. But there are common forces that we're going to encounter. And these common type of forces is what we call here the normal force. And the normal force is coming from a support. You're most likely now sitting on a chair, and that chair has to support you. And probably your computer or your laptop or your book is on a table, and the table has to support this. If the table is weak, the book or the computer will fall through because of the gravity. So surfaces always apply a force normal to their surfaces. Normal here meaning perpendicular to the surface. Meaning they make an angle of 90 degrees. So in this situation here, you can see the normal force and the supporting surface. The angle is 90 degrees. Now you have a surface here which is at an angle. And again, you can look between the force and the surface, and the angle is 90 degrees. So normal here means it makes an angle of 90 degrees with the surface, or we say the force is perpendicular to the surface. So in this situation here, it is perpendicular to the supporting surface. And in this situation here, where you have an incline, the force is also normal. This normal force is normal to the surface. And that's what we mean by a normal force. A normal force is perpendicular to the surface and pushes on the object out of the surface. Now, in this textbook, we're going to look at things always moving around the center of mass. So when you look here, we took the force here from the center of the mass. Now, you may see this in some different textbooks. They may actually go from the surface because they're saying that the surface is applying this. So it comes from the surface. But when we look at an object, the effect of the object always moving around the center of mass. So if you have a block like this, the center of the mass here in the middle, and that's why we drew the normal force from the center of the mass. The same situation here. The second type, which is friction force. And that also happens between the contact between the two surfaces. And friction always tries to slow your motion. So as you can see in this situation here, something resting on a surface, you see the normal force, which is coming normal from the surface and is pushing up. And we took it from the center of the mass. And friction here is basically opposing your motion. If you're moving this way, the friction is going to be in the opposite direction. In some textbooks, you may actually see the friction is between the two surfaces, indicating that this is coming from the surface. But again, I tell you, objects move around their center of mass. So we look at the net effect of this is basically coming from where? It's coming from the center of the mass. You may actually see it in some textbook that it's coming from the surface, but again, I tell you that things move around the center of mass, and that's why we look at this as coming from the center of the mass. Now, there is another common type that we're going to encounter, which is a tension force. Simply, we call it tension. We give it a symbol capital T. And again, you pull on an object, and always the effect comes from the center of the mass. And tension is always caused by a rope or a string or a cable or a wire, okay? And always it's acting away from the object because you are pulling. You don't push with ropes or cables or wires or strings. You only pull. So that's basically the common type that we're going to encounter. And then you have the weight, and the weight has to do with the gravity, because things are being pulled toward the surface of the earth. Even if they're resting on the surface of the earth, gravity is there. It's even if you try to move them up, you have to apply a force because the gravity is pulling on them. And that's what we call W, which is the weight. And again, it's operating from the center of the mass. If I go to the previous slide and I look at this one here, I can also add here another force, which is the weight as well. So you have, if it's resting on a surface, three forces can basically come from the surface. The normal force, which is the surface pushes up on the object, and the surface will feel the weight that's coming from the object on the surface, and that's why it has to apply this normal force in this case here. And the friction always acts between the surface and the object that's moving on it. So to complete this, we can add the weight here as well. So the common type of forces that we're going to encounter, it's either the normal force or the friction force or the tension or the weight. Is this clear? Now, whenever you are dealing with an object, you have to identify the forces that are exerted on this object. Some of them may be common type forces. Some of them could be applied forces. So usually we do that with something that we call a free body diagram, and we give the abbreviation here as FBD. So you have here, in this situation, a book on a table, and I want to identify the forces on it, then I have to sketch the forces that are on this object. And I told you we always do that from the center of the mass. So I come here and I say the weight is down, and I say the normal force is up. Okay. Now some of you may say, what is the friction? Well, the book is resting, so it's not moving. Okay. So there is no need in this situation to include it in, but that's how you do it. So usually to identify the forces, you make a sketch and you draw something that we call a free body diagram, because it's sketched freely by hand, and you identify the forces. Once you identify the forces, you can basically look at what is the effect of these forces on the object. And that's why here we deal with superposition of forces. Superposition comes from superimpose. So when you have two photos or layers and you want to put one on top of the other, we say superimposed. In forces, as we discussed earlier, we said the force is a vector. So when you deal with more than one force, which we say here, several forces acting on an object, then you have to get the combined effect of that. And the combined effect of that, that means you have to add all these forces, and you have to deal with them like vectors. And that's why we say here superposition of forces. So to do that, we identify the force that it's on the object, and in this case we have here, let's say F1, and we have here F2. So what is the combined effect of these two forces? Like what we did in chapter number 1, you add them like you're adding vectors. So you can either take F1 and you bring it here. So you're bringing the tail of F1 onto F2 on F1. And in this case, you're going to get a resultant force which will equal to F1 plus F2. Or you can take the tail of F1 and you bring it there. You put it on the head. And in this case, you will have F1 plus F2 as vectors. And that will give you your resultant force. So we can say here R will equal to F1 plus F2, if I'm taking this situation here. So you're dealing with them like you're dealing with vectors. So you're going to sum the forces. This symbol here means sum. That means you're taking the total. And at the end, you will have a net force. So the F net here should equal to the summation of forces. And that's what we call the superposition of forces. Now, you're dealing with vectors. And remember what I told you about how to add or subtract vectors in chapter number 1. I said you can basically do them graphically. That means you have to do everything to scale. Or you can sketch and do them with your knowledge of trigonometry. Or we said that you can break vectors into components and then you add the components together. So here we're going to look at things in 2 dimensions, meaning X and Y, as you can see here. So you have a force here, F, which makes an angle theta relative to the positive x-axis. And you can break this into an X component and a Y component. So your F here, as we discussed in chapter number 1, it could be the Fx plus the Fy. And as we did in chapter number 1, you can say that F here should be Fx I hat plus Fy j hat. So you're writing these in terms of the unit vectors here. And we took the vector sign from the x and the y. Now the x component, we define that as always F cosine theta, where F is the magnitude of your vector. And in this case, it's the magnitude of the force. So that's your x component here. And the y component is equal to F sine theta, and this is the y component here that you have in the force. And once you do that, you're basically going to add them. So usually, when you look at an object and you identify the force, you're going to set x-axis. Where is your x and where is your y? So it is advisable that these axes are perpendicular to each other, and that's what we usually do. X and y are perpendicular to each other, and z is also perpendicular to them. They make a 90-degree angle with each other. In the case of two-dimensional, x and y are perpendicular to each other. It is advisable to choose the x-axis along the motion. That will simplify things for you. And of course, in this case, the y-axis is going to be perpendicular to the motion. And that's exactly what you have here. This is your x-axis. This is the y-axis. But the actual motion here is happening along the x-axis. And that's why we chose the x-axis to be along the motion. And you have here the x component, and the y component, of course, is going to be perpendicular to the motion. So that's what we usually do. Then we're going to take the net effect of all these forces, which we call here the net force. So you're doing the vector sum of these forces. And this vector sum, which basically I told you that this sign here means a summation, and you're summing all the vectors, and that will give you a resultant force, and that will give you the net force here. So the summation of the forces should equal to F net. So the summation of forces here will be, if you have, it could go as many forces as you have. So F1 plus F2 plus F3. Now, notice that it is summed like a vector. For each of these forces, you can break it into an x and y component. So when you take only the x or the x component of the net force, that means you're summing all the x components. So you have here F1x, F2x, F3x, and so on. And you can sum, or you get the net y component of the forces, and you have here F1y, F2y, F3y, and so on. Like you're dealing with vectors. Now, if you want to get the magnitude, which is always the absolute value of the force, and in this case, it's the absolute value of the net force, and it will be the square root. And usually when you take a square root, you always have to have a plus or minus, but magnitude is always positive, and that's why we don't include that. We only taken the positive root. So it will be the x component squared plus the y component squared, and that will give you your magnitude of the force, which we write it here again as the x component of the net force squared, and here we write it as the y component of the net force squared. Under the square root, you take the positive, that will give you the magnitude of the force. you decide on the direction. And remember, we said we always take it relative to the positive x-axis. So we're after the angle theta here. And we say that tan theta is equal to Fy over Fx. So theta will equal tan inverse of the net y component over the net x component. And that will give you your direction relative to the positive x-axis if we follow this definition that we did in chapter number 1. And of course, you have to be careful if you are in the first quadrant, meaning the x component is positive, the y component is positive, you leave the angle as it is. If you are in the second quadrant, which is here, where your x component is negative and the y component is positive, the calculated result that you get from this equation here, you add to it 180 degrees. And if you are in the third quadrant, where your x component is negative and the y component is negative, you add 180 degrees. And if you are in the fourth quadrant, where the x component is positive but the y component is negative, you add 360 degrees. So first quadrant, you do nothing. Second and third quadrant, you add 180 degrees to the calculated theta. If you are in the fourth quadrant, you add 360 degrees to the calculated theta. And that's what we did in chapter number 1. So in handling forces, you have to deal with them like you're dealing with vectors. Is this clear? Any question on this? So let's illustrate this with an example here, and we'll look at example 4.1. 3 wrestlers are fighting over a champion's belt. The figure shows the horizontal force each wrestler applies to the belt as viewed from above. They ask us to find the x and y components of the net force on the belt and the magnitude and direction. So if you look at your x-axis here, this is the x, this is the y. F1 here has a magnitude of 250 newtons. They give you the angle here between F1 and the negative x-axis as 53 degrees. We always measure it relative to the positive x-axis, so you basically want this angle here. And this angle here will be 180 degrees because minus 53 degrees, and it will give you 127 degrees. So for your F1 here, which we have it here as a vector, the vector sign on the top, F1, which is magnitude, it's 250 newtons. Theta 1 here will be 127 degrees relative to the positive x-axis. F2 has a magnitude of 50 newtons. It's along the x-axis, so the angle between it on the x-axis is 0 degrees. F3, you can see the vector sign on the top. So the magnitude here is 120 newtons. And the angle that it makes relative to the positive x-axis, it will be this angle here. And of course, this angle here is 270 degrees. Now, the units of the forces here are a Newton. Later, I'll tell you what a Newton is equivalent to, but we use a Newtons as an SI unit for the force. Now, we want to get the combined effect of all these 3 forces. So we're going to look at F1, and we take the x component of F1. If we follow our definition in chapter number 1, F1x should equal to F1 cosine theta 1, which is 250, cosine 127 degrees, and that will give you minus 150 Newton. If y1, it is F1 sine theta 1, which is 250 sine 127 degrees, and that will give you 200 newtons. Now the F2x And again, the f2x should equal to f2 cosine theta 2, which is 50 cosine 0 degrees, and cosine 0 degrees is 1, and that's why you get 50 newtons. For the f2y, it is f2 sine theta 2, and sine theta 2 is 50 sine 0 degrees, and that will give you 0 Newton, and that's why you have 0 newtons here. The f3x should equal to f3 sine theta 3, which is 120 sine cosine 270 degrees, and cosine 200 is 0, and that's why you get 0 newtons here. And f3y equals to f3 sine, sorry, here it's cosine, sine theta 3, which is 120 sine 270 degrees, and that will give you minus 120 Newton, and that's what you have here. So now you have all the x and y components for all the three forces that you have here. So if you look at the x component of the net force equals the summation of all the x component, which is f1x, f2x, f3x, which is 150 minus plus 50 plus 0, and that will give you minus 100 newtons. Now the y component of the net force, which is the summation of all the y components, which is f1y plus f2y plus f3y, 200 plus 0 minus 120, and gives you 80 newtons. So that's basically the net x component is minus 100 Newton, and the net y component is 80 Newton. The y component is positive, the x component is negative. You are in the second quadrant. So this is your x component of the net force, minus 100 Newton. The y component of the net force, which is 80 Newton. If you want to find your magnitude, we already said that the magnitude should equal to the positive square root of the x component of the net force squared plus the y component of the net force squared, which is minus 100 squared plus minus 80 squared, and that will give you 128 newtons. So you got the magnitude of your force. Now you want to get your direction, and if we follow the definition that we did in chapter number 1, tan theta is equal to the y component of the net force, or the resultant vector, divided by the x component of the resultant vector. So you have here 100 over minus 80 over minus 100. So theta will be tan inverse of minus 4 over 5, because of course you take a factor of 20, and that will give you minus 38.6. And this is what we call the calculated theta here. I told you that if you use this definition straight relative to the positive x-axis, if you are in the second quadrant, which is we are in, which is basically the y is positive and the x is negative, you have to add 180 degrees to that. And it gives you here 141.4 degrees. So we're just repeating what we did in chapter number 1 when you deal with vectors. We're just reminding you again here, when you're dealing with forces, you deal with forces like vectors, and you have to break each force into an x and y component in 2 dimensions, and you add them up like you're adding vectors, and you can get magnitude and direction. Is this clear? Now, Newton's first law says the object is at rest. That means the object is not moving. Well, that means the net force on it is equal to 0. Very logical. So the object in this case remains at rest because the net force on it is 0. What if the net force acting on the object in motion is 0? So we don't want it to give you the wrong impression that force equal to 0 means that the object is at rest. You can have a net force equal to 0 and the object also in motion. So Newton's first law deals with the situation when the net force is equal to 0, but the object could be at rest and also could be in motion. Maybe this situation here can help us. You have an object on a table and you give it some initial velocity. You know that the object is going to move because you're giving it a velocity, but there will be a friction between the object and the table. And eventually this will stop. That means it's going to come to rest. What happens if I do that instead of a table, I put that on ice and I give the object an initial speed or initial velocity? It will travel further, but it will stop. And you know that this is basically coming as a result of friction. What happens if I put this on air track? Probably you've done this in the lab as well. And when you do that, you know that it will move further. And the idea here, if there is no friction, the object will never slow down. Meaning, you can have an object in motion and there is no net force on it. That's the idea of these three situations here. So Newton's first law states, in the absence of external forces, that means the net force is equal to 0, an object at rest remains at rest, and an object in motion continues in motion with constant velocity. So, for example, a situation where you can have an object on a surface, and in this case, you can have the normal force, you can have the weight, but the object is moving along the x-axis, but there is no friction. And in this case, we say that the net force is equal to 0. That doesn't mean there are no forces, but that's why we say here, in the absence of external forces. Okay. If it's at rest, it will continue at rest. It's moving with constant velocity. It will continue doing so. And when we say here the absence of force, that means something that it's applied on it. So when no forces act on the object, the acceleration will be 0. So if the object is at rest, the object is not going to move. Remember what we did when we talked about kinematics. We start from position. If you want to move, you have to have velocity. And in order to achieve velocity, even if you're starting from rest, you really have to have what? You have to have an acceleration to do that. But if the object is at rest, it's not moving, then your acceleration is 0. If the object is moving with constant velocity, also in a straight line, it also has a 0 velocity as well, 0 acceleration. And we say the net force in this case, it's equal to 0, and the object is in equilibrium. This is what Newton's first law is. It tells you that the net force on the object is equal to what? Is equal to 0, and hence the acceleration is equal to 0. And if the acceleration is equal to 0, then the object will remain at rest if it's at rest. If it's moving with constant velocity, it will continue doing so. In Newton's second law, we'll look at the case when there is a net force. So if you have this situation here, where the object or the puck that we have here is moving with constant velocity, and if you look at the diagram here, you look at the green arrow, and the green arrow here, and the green arrow here, having the same length. That means they have the same magnitude, and they are in the same direction. Same magnitude, same direction. That means the velocity here is constant. That means your acceleration is constant. And of course, the net force here will be what? Will be 0, in accordance with Newton's first law. What happens if you have a net force on the object? When there is a net force on the object, now if you look at the green arrow here, indicates your velocity, and you look at the second situation here, you see that your velocity has increased in magnitude. You always need acceleration to do that. And this net force has resulted in acceleration. And you can note here that the acceleration here is in the direction of the motion, which is parallel to the net force. Now, in the second situation here, or the third diagram that we see here, you can be basically moving in this direction, and you have a velocity. Notes that the length of your arrow has decreased. That means you're slowing down. And remember what we talked about when we talked about kinematics. If your acceleration and your velocity are in the same direction, in straight line, you are basically speeding up. And if your acceleration opposite to your velocity, you will be slowing down. So you can see that you would have an acceleration opposite to your velocity in order to slow it down, and that of course comes from the applied force, which is applied along the or opposite to the direction of the motion, but you still see that it is parallel to the force, and the acceleration are parallel, meaning that the force and the acceleration in these situations are parallel to each other. Now, what happens if I want to look at the mass? So let me take a situation where I'm using a puck with mass m, and I apply a force here which is equal to F1, and I measure the acceleration. I will measure acceleration A. Now I will change the mass with, I will keep the mass, and then I double my force. I will find that my acceleration doubled. if now I take half or apply half of the force and I keep the mass the same and I measure my acceleration, I find that I get half the acceleration. Right away, I will find out that the net force is directly proportional to the mass, directly proportional to the acceleration. You increase the force, you increase the acceleration. You decrease the force, you decrease the acceleration. But in this situation here, just to look at one effect, which is the effect of the force. But I put that an object. That's why we kept the mass here constant. I only want to look at the effect of the force and measure acceleration. Now, in this situation here, I want to look at the effect of the mass. So what we're going to do is we're going to keep the force constant, but we're going to change the mass. So you take mass 1, you apply the force, and you will find acceleration is equal to A1. Now, in the second case, you take a different mass, which is M2. You apply the same force, you measure a different acceleration now, it's A2. So the mass affects the acceleration. Now, if I combine the two masses, M1 plus M2, and I apply the same force, I will measure a different acceleration. And you find out that this acceleration, if you look at the arrows here, it is longer, then less, and then less. That means the magnitude of your acceleration decreases as the mass increases. So we say that the acceleration is inversely proportional to 1 over m. The bigger the m, the less is the acceleration. So Newton's second law states the following. The acceleration of an object is directly proportional to the net force acting on it and inversely proportional to the mass of the object. If we take the proportionality constant out, we find out that the force is equal to ma. Again, note that there is an arrow on the top to indicate that the force is a vector. The mass is a scalar, but what is a vector is the acceleration. So the vector sign that we see here and the force comes as a result from the acceleration vector. And whenever you have a vector in 3 dimensions, the vector will have an x component, and the sum of the x component, which will give you the x component of the net force, will equal to max, and that's the resultant acceleration in the x direction. And the y component of the net force, which is the sum of all the y components, will give you may, and this will give you the acceleration along the y direction. Similarly for the z, the z component of the net force, which is the sum of all the vectors, will give you maz, where the az is the z component of the acceleration in the z direction. Now remember what I told you, that we use newtons as a unit for the force, SI unit. Now we can express what it's equal to. Since the force is equal to ma, and m has units of kg, which is kilogram, and the acceleration have units of meters per second squared, So 1 Newton is equal to 1 kg meter per second squared. So 1 Newton is equal to 1 kilogram meter per second squared. So in SI units, we use newtons to measure the force, and we use kilogram, which is kg, to measure the mass, and acceleration is measured in meters per second. And the SI unit sometimes is referred to as the MKS, where M stands for meter, K stands for kilogram, and S, it stands for second. There is another system which we call CGS, and CGS, that means centimeter, a gram, and then the second. And you know that the meter contains 100 centimeters, the kilogram contains 1,000 grams. So the force will be measured in a unit that we call dyne. The mass will be measured in grams, and the acceleration will be measured in centimeters per second squared. So if we look at the Newton, which is equal kilogram meter per second squared, now if you want to convert that into centimeters, grams, then you will have 1,000 times 100. So it will give you about 100,000 grams centimeter per second squared. And that's why we say a Newton is equal to 100,000 dynes. So we say 1 dyne here is equal to 1 gram centimeter per second squared, but it's equal 10 raised to the power minus 5 newtons. So 1 Newton contains 100,000 dynes. Now in the British system, they use pound for force, they use a slug for mass, and they use feet per second squared for acceleration. But of course, most books nowadays, they use the SI units. But if you encounter different textbooks or situations when these units are used, you understand what they mean. Is this clear? So that's basically what we mean or explain now. A Newton is equal to 1 kilogram meter per second squared, and the unit is named after a Newton to honor Newton and to make his name lives, because he's the one who was working or basically stated these 3 laws of motion. Now let's apply these to some examples. And the examples that we have here, you have a worker applies a constant horizontal force with magnitude of 20 Newton to a box with mass 40 kg, resting on a level floor with negligible friction. What is the acceleration of the box? Well, remember what I told you. Everything moves around the center of mass. So the first thing that you're going to do here, you're going to look at X and Y. Where is your X and where is your Y? X has to be along the motion. Directly, Y will be perpendicular to it. So we come here to the center of mass and we put our x-axis. Perpendicular to it is our y-axis. Second thing, free body diagram. Identify forces. Now I told you always take the effect from the center of the mass. So the weight is pulling down. The normal force that's coming from the floor is pushing up. That's along the y. And along the x-axis, I only have the applied force of 20 newtons. So if I want to look at my force, the summation of the force, which is equal to the net force, should equal an x component, which is equal to max, a y component, which is equal to may. Now, along the x, which should equal to max, I only have the applied force, which is 20 Newton, and it's going in the positive x direction. So that's why here we have the F applied is equal to max, and ax here will equal to F divided by m. The F is 20 Newton. The mass is equal to 40 kilogram, and 20 divided by 40 will give you 0.5 meters per second squared. Of course, the summation along the y, in this situation here, you have the normal force up, the weight acting along the negative y direction, that should equal to may, but there is no motion along the y direction, and that's equal to 0. So the only acceleration or the only motion is happening along the x-axis, and this is basically the ax. Is this clear? Any question on this one? Another example here. A waitress pushes a ketchup bottle with mass 0.4 kilogram to her right along a smooth table. The bottle leaves her hand, moving at 2.8 meters per second. Then it slows down and slides because of constant horizontal friction force exerted on it by the countertop. It slides for 1 meter before coming to rest. What are the magnitude and direction of friction force acting on the bottle? So now this is the situation. The bottle, which has a 0.45 kilogram, it has an initial x component of velocity of 2.8 meters per second. And finally, it stops with Vx is equal to 0, but it stops after 1 meter. And they asked me to figure out the friction force. Now, as I told you, first thing is xy, and x has to be along the direction of the motion, so that's your x here. And y, of course, will be perpendicular to it. I do my free body diagram, and the free body diagram tells me that I have the weight which always acting toward the center of the earth, perpendicular to the surface of the earth, the normal force which is perpendicular, in this case to the surface of the table, and there is a friction, and a friction is opposing the motion, and we took all of these from the center of the mass. So if I want to do that, I know that again, the net force should equal the summation of the forces. And in that case, you will have the summation of Fx, which is equal to max, the summation of Fy, which is equal to may. Now, in your situation here, along the y, there is no motion. And we dealt with this in the previous example. The only thing, everything is happening along the x. So what I have here, I have the summation of Fx is equal to max. Now, I look at the forces acting along the x, I only see friction. And friction is acting along the negative x direction. And that's why you say it's minus F here. And that should equal to max. Now, this is what I want to find. I want to find the F here. And I'm given the mass, but I don't know what the acceleration is. I have to figure out the acceleration. Now, in the problem, I'm given that the V0x is 2.8 meters per second. It travels for 1 meter and then it stops. From kinematics, I know that Vx squared equal to V0x squared plus 2ax delta x. where delta x here, it's x minus x0, as we did in chapter number 2. Now, my final velocity after 1 meter is 0, and my initial, it's 2.8 squared plus 2ax, and of course, my x is equal to 0. I can take my x initial equal to 0 here, so you have 1 meter. So out of this equation here, you want to find the ax. So you can take this to the other side with a negative sign. So you have ax will equal to 2.8 squared, and you have to divide by 2, and it gives you that the ax is equal to minus 3 meters per second squared. Now this equation here tells you that minus f is equal to max. Your f now, I can multiply the minus out, so f will equal to minus max. So it is minus 0.45, and the ax is equal to minus 3.9, and that will give you 1.76 in newtons. So the magnitude of the friction force is equal to 1.7 newtons. Now you may ask about the direction, because they ask you about magnitude and direction. So here it's f as in magnitude. The direction here, theta, which is, we can take it relative to the positive x-axis, it will be 180 degrees because it is opposite to the motion. Is this clear? Okay. Now we'll deal here with 3 questions where we try to discuss what we learned. The first question here, an elevator is being lifted at a constant speed with steel cable, so pay attention here to a constant speed. A steel cable attached to an electrical motor. There is no air resistance, nor there is any friction between the elevator and the walls of the elevator shaft. The upward force exerted by the elevator in the cable is. So they were looking at this upward force, and you can basically talk about this as being the tension here. And they give you these options here. So you can tell me what is the right answer here, as I'll try to discuss. You can look at this and give your answer. Now, remember, we said that the first thing that you're going to do is you do an x and y. And we said that x along the motion. But here, if you look at the situation here, you say, well, I'm going to make my x-axis this way and the y-axis this way. We always took y as being vertical to the surface of the earth. Okay. And then the second, we said we always do a free body diagram. Okay. So the free body diagram here, you have the tension, and I will have to look at the elevator. That's what I'm interested in. And you do that from the center of the mass. That's of the tension, and down is the weight. And then you're going to look at your Fx. And your Fx here, you don't see any forces here in the x. And that should equal to max, which means 0 equal to max, meaning ax is equal to 0, and there is no motion along the x in this situation. But if you look along the y, you will have the tension acting up, positive, minus the weight, which is acting down, equal to may. But they told you that you are basically moving with constant speed, up. That means your velocity in that direction is constant, meaning that the a is 0. So the ay here will equal to 0, meaning that t minus w should equal to 0. And that will tell you that t is equal to what? Is equal to w. So out of this option here, you will say that the exerted force by the cable, which is the tension here, T, will equal to the force of gravity, because the weight is basically due to the force of gravity, and the right answer here is B. In question 2 here, they give you a VT graph. And they ask you which one of these force T graphs will represent this. Now, we know that when we talked about the F, we said it should equal to MA. In this situation, we only have X, because they give you Fx here. So you look at Fx equal to MAX. So I need to get the AX. So I have to shift from a VT graph to an AXT graph. And if you take the slope of this one, it will give you 0. Because when you do that, you always remember when we did in chapter number 2 and 3. This one will give you an acceleration, and it's a constant value here. And then it will drop back to 0. So when you look at your Fx, which is equal to MAX, M is a scalar quantity, so you're only looking at the AX. And since this is your AX, so that's how your F of X versus T will be. So the only answer here will be what will be E. Is this clear? And the third and final question here, you have two masses. One is 4, the other one is 6. They're connected by a cable, and they tell you the rope remains stretched. And a lady applies a force. And they ask you here, compare it to the 6 kilogram crate, the lighter 4. So you want to compare the 4 to the 6, and they give you these options. Now, the way you look at this is a system now. And they tell you that the cable here is stretched. That means both of these masses are moving with the same velocity. It's a system. So they move with the same velocity. And if they're moving with the same velocity, they must have the same acceleration as well. And that's the acceleration of the system. Now, I can look at each object differently now. I can look at 1 and 2. And since the motion is along the X, so the net force on 1, which I will call it here, the summation of F1 along the X will equal to M1AX, and the summation of F2 along the X will equal to M2X. Okay. So since the acceleration is the same in both cases, but M2 is less than M1, and I'm trying to compare the 4 to the 6, which means 2 to 1, then I would say that the net force on 2 is going to be less than the net force on 1. And that's why the option here is B, is subjected to a smaller net force and has the same direction. Is this clear? So in summary, what we have accomplished today is basically we looked at a force as a vector, and you add them like you're adding vectors. In Newton's first law tells you that the net force is equal to 0, which is the system is in equilibrium. And Newton's second law tells you that the force is equal to MA. And again, you note the vector sign here, the vector, and the vector here comes from the A, okay, not the M. The M is a scalar quantity. And that's why when you look at the x component, it's only ax, m is a scalar, the y component is a y, and the z component as a z. And that's basically what we tried to accomplish today. Is this clear? Any question on this? Good.